Hello everyone, my name is Amir Senahri. I'm a Google Earth Engine expert, and here I'm going to show you how to calculate the water area for the inland waters and also the lakes. Let's go to the Google Earth Engine platform code editor. Here I'm going to show you to calculate lake area by JavaScript in the code editor, and then for the first step we should identify the study area. My study area in this tutorial is the Urmia Lake in the northwest of Iran. By the drawing tools here, you can set your study area, for example, geometry, helping me to draw the study area first, and then we can start programming in the code editor. Map.center object helps to have focus on the study area or the location of the interest, and the location of interest already entitled as geometry in this bar, as you can see here. In the next step, you need to call your desired satellite data. There are different satellites data enabling us to calculate the lake area, for example, Landsat, MODIS, Sentinel, and on it goes. But the most important or the most applicable satellite images nowadays we use for calculate lake area are MODIS and Sentinel, and also the Landsat series data. For example, here I'm going to use Landsat images. The process of programming is same for Landsat, MODIS, and Sentinel. Just you should know about the bands and also the threshold and how to set them. If you had any questions or any problem regarding to the programming steps, you can add your comments in my YouTube page, and then I will back to you and answer them and help you to solve the problems. So first of all, I make a variable for the Landsat images entitled Landsat equals to. Through the search places and data set, we can find Landsat collection 2 level 2 data. Here, if you type Landsat 8, for example, Landsat 8 collection 2 level 2, helping you to find the dose of Landsat data, which is radiometrically and atmospherically corrected. Landsat collection 2 and level 2 is the newest product, which is available in 2024, enabling us to have Landsat images with great quality and no need to any atmospheric or radiometric corrections. Just you have to implement or apply some scale and factor to receive the surface reflectance value. It's wonderful for the calculations and doing image processing by Landsat images. So by the import image collection, Landsat image collection imported to the code entitled as image collection here. Then I write image collection, or I assign image collection to the Landsat images. And for all of the satellite data you are going to do calculations in the Google Earth Engine platform, you have to set filter bounds and filter date, which is very important filters, and before any programming you need to define this. So that filter date enabled us to call satellite images for a specific period. For example, I make two variables like time start and time end. Time starts like this. Time start equals to, for example, 2020. I want to get the area of the Urmia Lake in the northwest of Iran for 2020, and time end would be here 2021. 2021. For the 2020, I want to get an average Landsat images and then calculate the lake area for this region. So filter date starts with time start and time end, just like that. And then dot filter bounds enabled us to limit or narrow down Landsat collections to the region of the interest that already defined here. The filter bounds is a geometry like this, and then by select you can call your desired bands for the calculations and also the computations or something like that. So for now, just I want to write print like print Landsat collections to see how many images are available for the 2020 from Landsat scenes for this area. As you can see, for these regions, only 12 elements are available, and also it's a little weird. I think there is a problem in calling a Landsat data. Oh, the problem is here. I should call Landsat 8 collection to level 2 tier 1, not 2. So that's the problem. Collection 2 tier 1. So just like that. And we remove collection, the collection already imported. And then if I run code again, you can see 98 elements are available, 98 images are available for the 2020, and you can see different features and also different dates, and also the different frame code, and also pass and rows showing here. And each features included 19 elements, included surface reflectance bands, and also the complementary bands that are useful for do some calendar calculations or something like that. We don't need them, just we need some multispectral bands from visible and near infrared regions to calculate normalized difference water indices to separate or mask all of the non-water pixels from the satellite image. So back to the programming. So far we defined filter date and filter bounds, and in the next step I need to do some process on each collection or on each element or on each feature during the time series to select the desired bands to calculate the desired spectral indices such as normalized difference, water index, or something like that. To do this, we make a loop by .map functions. .map works very well and enabled us to do calculations over the time series images. .map, in the map, define a function. Each input images considered as an img here, and then in the parentheses we can, in the new parentheses, we can write the specific or any considerate equations that we need to do on each input images in the collections. First of all, I need to select specific bands and implement a scale and factor that already defined for the Landsat images. Variable bands equals to from each imported image into the collection or into the loop, which is entitled already as an img dot select. I selected the surface reflectance bands. All of the surface reflectance bands starting with SR and underline, as you can see, and I write to select those of bands starting with SR underline, and then to include all of the bands starting with this prefix type dot and this sign here, and then dot multiply and dot add help us to implement the scale and factor. What is the scale and factor? If you go to the data descriptions in the Google Earth Engine data catalog, there are descriptions, and also in the bands. In the bands you can see every bands, all of the bands listed here, and also here we have a scale and offsets that we need to multiply each images on own scale and own offset and add to own offsets. Just copy a scale value to the code and multiply to the scale, and the offset value was minus 0.2. The scale and offset for the surface reflectance bands are same, and also no need to change it for the different bands, because we only need to do calculations based on the surface reflectance bands and no need to the thermal bands or something like that. So that's the first equation, or that's the first variable that selects surface reflectance bands and implement scale and factor by multiply and add functions. It's a linear equations actually that needs to be applied on each band before any further processing. So in the next step, you should define or you should calculate the normalized difference water indices. The normalized difference water index NDWI enable us to highlight the water and inland lakes in the satellite images. A variable NDWI, normalized difference water index. It's very simple. It's a normalized equations. Just we use bands dot normalized difference, just like that. It's a normalization relationship between the near infrared and red, just like NDVI, but in the NDVI we have a normalization between near infrared and red, but here the normalization is between green and near infrared. So the green band is band number 3, surface reflectance 3, and near infrared band is surface reflectance band 5. Oh, sorry, my mistake. So band number 5 here selected, and then by rename I use, for example, a new name for the NDWI images. So this is NDWI, normalized difference water index, and then return NDWI as a final calculation in each date, and then copy. We need to have the properties of each input images to the output. What is the properties? As we talked about that previously, in each feature we have different bands, and for each features we have different properties. The properties including the metadata informations, the time of acquisitions, the scale and factors values, and the system time start, system time end that are necessary for the time series analysis in the Google Earth Engine, or different informations that you can see all of them listed here and available for all of the satellite images. So now we need to copy or have all of this information for the further processing if you want to do the time series analysis or something like that. But in this tutorial it doesn't matter if we don't have them. But however, I use the copy properties here to copy these kind of properties from the input images for the all NDWI images that already calculated. Dot copy properties from img names. It means take all of the property names and copy them to the new outputs that we calculated before. So if you can save your code, and also you can run it, it doesn't matter. Execute code by run, and here again we have 98 elements, and throw the 98 elements in each date. Now we have one image entitled as normalized difference water indices. That's the first step. In the next step, I need to select those of Landsat images with the lowest, for example, cloud cover. And to do this, in the properties, we have some information about the cloud cover in each scene. For example, here we have cloud cover percentage. That's mentioned here. For example, this image contained 47% of image covered by the cloud, but we need to call those of images which are almost or approximately cloud free, and to do this we need to define a new filter or less than filter. Here dot filter, for example, I add a new filter, filter Earth Engine dot filter dot lt. The filter for less than. We need to filter input image collections based on the cloud covers less than a specific threshold. Less than, the property is cloud cover. From the properties I select the cloud cover, and I say that I need those of images with cloud cover less than, for example, 10%. Totally cloud free, because to have accurate the area value for the lake, we need to have all of the pixels clear without any noise, and also very perfect for the calculations to reduce the amount of the uncertainties that may occur by the cloud cover or something like that. So if click on the run again, here we have after filter cloud cover, you can see that only 47 elements are available, and these are almost cloud free images. And then we can make it we can get a median value from all input images to have a single band. That's median. If you want to, for example, narrow down your calculation for a specific period in during a year, you can use the calendar range, just like that. For example, I want to use those of satellite data belongs to, for example, summer season. Accordingly, earth engine.filter.calendar range helps me to select the specific months during a year to collect their data and do calculations based on. If you want to have focus only for summer or only for winter, just in the calendar range, you can choose your desired period. For example, from June to September, I selected here, and based on the months, from months number 6 to months number 9, from June to September, I want to call Landsat images, those of Landsat images with less than 10% cloud cover here, and then get a median of all of the summer images. And you can use different types of the statistical operation instead of the median, like average or minimum or maximum or something like that. But here median is very helpful because it reduces the effects of the remains clouds and also the shadow effects in the satellite data, which is very, very useful for specifically in the mountainous regions and also some regions that are really, really cloudy. So then if I print again, you can see that we have one median images from the cloud-free data for the summer of 2020. And now if you want to see the final image, here you can use map.addLayer. Map.addLayer helping us to visualize the Landsat images calculated, and then I want to clip it based on the geometry already drawn. And then for the visualization, I leave it free, leave it empty here. And then for the name of the data sets, we can set a name, for example, Landsat Summer, or NDWI Summer is a name of the image that we want to visualize it. And then insert false. False helps us to manage the visualization process. For example, when you run your code, but here we have a problem before. Yes, it's a Landsat. Yes, when you run your code, false helping you to control the visualization process. If you don't use false, the image automatically showed in the Google map or the map display that we have here, but false enabling us to control the visibility or non-visibility of the final images. You can choose when visible or when not visualize it. So if you zoom in on your study area, you can see the NDWI calculated for this region, and you can see that the image is available by the inspector. You can check the different values in the images. NDWI is very helpful to extract the water area from other phenomena or the land covers in your study area. It's a global index for the inland lakes that's already developed by the McFitter, and also it's one of the most cited spectral indices in the remote sensing that helps you to make it differentiate between the water and non-water pixels. Here, if you click on, you can see that the value of the water is those of values above 0. From 0 to 1 we have water, and also this is the specific range. But those of non-water pixels, for example, you can see that cleared or can be seen by the minus values, or those of values below to the zero value actually here. So now we need to set a threshold to differentiate or mask the non-water pixels from the final images. For example, here I can set a mask, I can copy map.addLayer into a new line, but in this time we want to show the threshold values applications here. For example, here after clipping process, we want to select those of pixels that cover the inland lakes or the water area. So we need to select those of pixels greater than 0.1 or greater than 0, just like that. So again, run the code, and this is the NDWI already calculated, and this one is the mask we created for the inland lakes, and you can see that we mask the non-water pixels by the thresholds, and here we can see that those of values greater than 0 is a suitable threshold to make a separation between the lake and non-lake areas. So to calculate the lake area, first of all, we need to make a threshold just like that from the Landsat image median for the summertime 2020. We want to select those of pixels greater than 0. So, and then in the next step, we should define a mask. Mask process enables us to remove the 0 values for the calculation of the lake areas. So actually here we have a dark regions that all labeled by 0 value, but we can remove them or turn them to the none values by the update mask function in Google Earth Engine. Here we get a THR or threshold image, and then using the update mask by threshold we can see the study area without the dark region. So again, by map.addLayer you can see the result of the computations here. Map.addLayer, here we want to see the mask already computed. So, and instead of NDWI THR we have NDWI Mask. So again, execute your code, and here we have NDWI Mask that remove all of the 0 values. So as you can see by the inspector, you can see that the lake area or the regions covered by the water, all of them labeled by 1, and non-water pixels are labeled by none. And in the next step, we need a function to calculate the area of each pixels. Just like that, here we make a new variable entitled as pixel area. For example, here we have a new variable pixel area equals to get a mask, and mask dot multiply, and multiply here means implement the new functions. The new functions is that Earth Engine dot pixel area, Earth Engine dot image dot pixel area. The pixel area is a function, as you can see, generate an image in which the value of each pixels is the area of that pixels in square meters. It's very important things, and it's very helpful for doing the calculations, doing that pixel area, and it is based on the square meter. But if you want to convert it to the square kilometer, you can do divide it to the 1e6 or 1 million to convert it from the square meter to a square kilometer. So next we use map.add_layer again. Using the map.add_layer, you can see the area of each pixel with the based on a square kilometer. So just here we have the pixel area, that click geometry and remove the threshold. Instead of NDWI THR, NDWI pixel area we have. So run code again. NDWI pixel area is the same image with a darker color, but the color doesn't matter. The only thing matter here is the pixel area. The pixel area is based on the square kilometer. If we remove the divide 1 million and run your code again, you can see the pixel areas by the with actually a square meter. Here you can see that this is the square meter, the area of each pixel, not the size of each pixel, the area of each pixels based on the square meter showed here. And then in the next part we need to calculate the lake area by the reducers functions. So here we make a new function entitled as lake area. Lake area equals to pixel area dot reduce region. So there are different arguments. For example, one of them is reducer. We want to get the summation of, or we want to get the sum of all pixels area for the selected regions. So here the reducer will be dot sum. For the location of interest, I think, which is a geometry, the argument is geometry, and the location of interest already entitled as geometry. And the next is scale, the scale of Landsat images defined based on the spatial resolution. The spatial resolution in Landsat data, as you know, is 30 meter, so scale should be 30. But for those of region which is a little big, sometimes scale 30 makes some problems or issues for the computations or something like that. In such cases, we need to increase the value of the scale if we face any issues regarding to the computation speed or something like that. We will check it. If we get error, we can increase it to 100 or 200 or something like that. But such kind of error just sometimes happen for some of the lakes or some of the study areas which are very large regarding to the processing that we are doing actually. So this is it, and that values we want to select the values from the first band and show that in the to show the final result in the right panel or in the console part. We need to print the final results. The final result will be lake area. Then if you run your code, oh yes, you can see that too many pixels in these regions. That's what I said before. We can increase the pixel size for scales here. I hope it works. Such kind of issues is very normal during the computations or something like that. Yes, you can see that the area of the lake based on the square meter calculated. If you want to convert it to the value, you can use the to the number from an object. You can use Earth Engine.number just like that, And if you want to get the value, get the area value as a square kilometer, here you can, as I told you before, we can divide the pixel area to 1 million. Oh, just 1e6, not 16 actually. Yes, the number is 3000 square kilometer. And also the threshold we defined is very important here. For example, if you increase the value of the threshold in the computations, sometimes helping you to make the final results more realistic. Again, with the new threshold, you can see that we get this value, 3000 square kilometer for the region of the interest or for the lake of interest. And then you can use this code for different lakes in all around the world. For example, I can just you need just change your study area. For example, another lake is in Turkey. You can see that this is another lake here, and we run the code for the new region, and you can see the area of this lake with the number format in the right panel. And also, for example, this is like that, 3000 square kilometer, and you can see that how much it is accurate for this region. This is NDWI image for summer, and sometimes for some images we face some bad pixels or noises or something like that. And then I try for another region, and also we can also change the time. Or for example, I try to set a longer period of time for the computations, because more pixels are available, and the possibility of NaN values and also the cloud covers and the noises reduced in the computations, and we expect to have more accurate calculations in this regard. For example, this is NDWI summer. You can see that, yes, now we have lower noises in the final images. And also the threshold works very well. Some years, because of the noises or limitation of the data or cloudy situation, we will have some gaps in the computations. By changing the timing period, cloud cover, or something like that, you can increase the accuracy of the computations. Yes. I hope this tutorial helping you to calculate inland lakes or water bodies in your works and also in your projects. If you faced any issues during the programming, just feel free to contact me through my YouTube channel. My name is Emerson Ahuri. I'm a Google Earth Engine expert. I will be appreciate if you like or share this video with other researchers who need to calculate the lake area for their process. And also in the next tutorials I will try to make a video about showing that how we can calculate the lake area in the time series, which is very helpful for the hydrological studies and climatological studies. Thank you for watching.